We spoke before about matrix representations of operators and wave functions. We thought of a wave function that just depends on the coordinate x as a vector by giving the entries of that vector being the values of the function at different points that were closely spaced. In all accuracy, you would need infinite number of points, and therefore a function would be represented by a column vector that is infinitely long. In that picture, we do represent the operator x, the position operator, as an infinite diagonal matrix. So the question remains, how do you represent the momentum operator, which is the derivative? And I want to show you how you can do that. In some ways, this representation is not unique, and as you will see also, it's a little subtle to see how you can think of the derivative as a matrix, in the sense that you get an answer that is accurate, or it's exact, only in the limit as the spacing goes to 0. And as long as you keep the spacing different from 0, which is what you probably need to work with this matrix representation in a computer, you can speak about representing the operator, momentum, or derivative with greater and greater accuracy. So we're going to be talking about matrix representations of x and p. Matrix representation of x and p, the operators x and p. And as we said, we're going to be talking about a wave function. X at this moment is going to have no units. Let's simplify matter, x with no units. And if you have a wave function, you can represent it, as we said, by a column vector. So I will write, say, some function of x that represents a wave function. It's a column vector, and I'll put f of 0 here in the middle, f of epsilon, f of minus epsilon, all the way down and up. So we're talking about thinking of this function by giving its values on the x-axis at intervals of length epsilon. And that's how we construct a matrix, a column vector. Now we want to think of the position operator, the x operator. What does x do? We said it just multiplies the function by x. So x, f of x, would be minus epsilon, f of minus epsilon, 0 times f of 0, epsilon times this. So if I think of it as a matrix, I would have that x would be epsilon times a diagonal matrix. And in these diagonal matrices, or in these matrices that I'm writing, the indices run from, not from 1 to infinity or 1 to infinity. It's more convenient, perhaps, to let them run from minus infinity to plus infinity. So at the center of this infinite matrix lies the matrix element that is going to happen, the center of this vector. So I'm going to say here that we have epsilon, so you have 0 here, minus 1, all the way minus 2, all the way down, 1, 2, all the way down here, and big 0, and big 0. So this matrix, as it acts on this column vector, will multiply the function by the value of epsilon at which the function is evaluated. And if you were doing this in a computer, this would work very well, in that if you represent your matrices by, say, 5 by 5, so you have this element in the center and 2 more rows and 2 more rows, and here you would have 5 entries, so you go from minus 2 epsilon to plus 2 epsilon. You could multiply and everything would go well. So here's the x operator, and now you can ask, how do I represent the derivative operator or the momentum operator? So the momentum operator, P, is h bar over I ddx. I don't have to write partials at this moment. I'm working just on the line, and x will have nothing to do with t. So just write it like that. Now, we don't want to bother with units. So the thing that must be the heart of the matter is, how do you represent ddx? ddx is a derivative of a function. How can we see it as a matrix? Well, we will. And the way we do that is thinking how the derivative can be evaluated on a function described in this way. So we're going to aim for just trying to understand ddx. What is it as a matrix? So, well, it's not too difficult. So if I want to, for example, calculate the derivative of a function at x equals 0, this function at x equals 0, ddx of f at x equals 0, I could do it in many ways. I could take the value at epsilon, subtract the value at 0, divide by epsilon, and that would be a fine representation of the derivative. Now, we're doing everything a little more symmetrical, so I'd rather do things more symmetrically as well. So I'll take this to be the limit as epsilon goes to 0 of f of epsilon minus f at minus epsilon divided by 2. Because indeed, f of epsilon minus f of minus epsilon with a Taylor series expansion, f of epsilon is basically f of 0 plus epsilon times the derivative at 0. I have to put an epsilon as well here. So now I got it the right way. I could put, this is limit as epsilon goes to 0 of 1 over epsilon times 1/2 f of epsilon minus f of minus epsilon. Now, indeed, this is good, and it's a good approximation if the higher derivatives are not too big. So let me pause a second before attempting to go further and write a little more general expression from which this follows, and you can use it to understand how you could do better than we're going to do, which is something we will leave as an exercise. So f of epsilon by a Taylor series expansion would be f at 0 plus epsilon times f prime at 0 plus 1/2 epsilon squared times f double prime at 0 plus 1/6 epsilon cube f triple prime at 0. I'll go one more, plus 1/24 epsilon to the 4th f. Instead of putting 4 primes, I'm going to put a parenthesis 4 at 0, plus order epsilon to the 5th. No, yeah, epsilon to the 5th. If I go here, I can write also what is f of minus epsilon, and that's f of 0, and the even powers of epsilon remain the same. The odd powers change sign, so you change sign for the first derivative, you don't for the second, you change again for the third, and you don't for the fourth. Epsilon to the 5. And indeed, if you subtract these two, f of epsilon minus f of minus epsilon, well, the even powers cancel, but the odd ones don't. So this is 2 epsilon f prime of 0. Then the evens cancel, and here you have plus, you're subtracting, so you get plus 1/3 epsilon cube f triple prime of 0. And the quartic terms in epsilon cancel, so this is plus order epsilon to the 5th. So from here, you see that indeed, if you divide by epsilon, maybe that's, let's divide by 2 epsilon. 1 over 2 epsilon, f of epsilon minus f of minus epsilon is equal to f prime at 0. We're dividing by 2 epsilon, so you get here plus 1/6 epsilon squared f triple prime of 0 plus order epsilon to the 4th this time. So here is a nice equation that justifies what I was saying here, that it's the first derivative is this limit, and it does more than justify it, it gives you the next correction. So this is accurate, but for epsilon finite, there's a small error controlled by the third derivative. So you may try to do better, but for finite epsilon, you can try to do better, and it's interesting to do that. But at this moment, we'll have that over there. It's also interesting to notice from these two relations that there's a simple way to get a hold of the second derivative of a function. Something that is interesting because the Schrödinger equation has second derivatives with respect to x, and you may want to think, how does the Schrödinger equation look in matrix form? So let's look at this, and if you add these two, however, you get f of epsilon plus f of minus epsilon. You add them together, you get 2f of 0. So I will actually, on the right-hand side, you get, well, 2f of 0. And then you get the order epsilon terms cancel, but as you can see here, when you add them, the order epsilon terms cancel, but the order epsilon squared don't, and you get an interesting term, plus epsilon squared f double prime at 0 plus order epsilon to the 4th. So actually, if you divide by epsilon squared, let me do the following. Do f of epsilon minus 2f of 0. I pass this term to the left-hand side, plus f of minus epsilon, divide by 1 over epsilon squared. That is equal to f double prime of epsilon at 0 plus order epsilon squared. So the second derivative of the function can be obtained by doing this operation, and this will be useful for us at some point in the future. It's a nice way of thinking of the second derivative. But our goal was really to think of the first derivative, and the first derivative is thought of by doing this operation. So let's try to think of the matrix representation of the first derivative. So how would I represent d dx as a matrix? Well, as a little crutch, here's the center of the matrix. Remember, it runs from minus infinity to plus infinity. And here's the center of the matrix. And here, if you want to imagine, you have f at 0, f at epsilon, f at minus epsilon. And you have the ghost of the function there. I'm just using it as a crutch. What am I supposed to do to get the derivative? I'm supposed to take 1/2 of the value at epsilon and subtract 1/2 of the value at minus epsilon. So I don't do anything with the value of the function at 0. So as a matrix here, I would have to put a 0 here, a 1/2, and a minus 1/2 here. 3 elements that when you multiply now this row by this column to get the derivative at 0, you would be combining minus 1/2 of the value of the function at minus epsilon, nothing of the value of the function, and 1/2 of the value at plus epsilon. So that would do it, and you must do the same thing for every value of epsilon. So I have to extend this matrix, and you must do the same when you're evaluating at the derivative at minus epsilon, which would be one row. What would matter would be one row above this one. You must include the value of the function at minus 2 epsilon and the value of the function at 0. So it will be shifted a step to the left. It will start multiplying a little earlier. So at the next step, it will be minus 1/2, 0, and on top of this one, 1/2. At the next row, it would be minus 1/2, 0, 1/2. And everything else is, of course, a big 0. But that's the form of the derivative matrix. If you've never seen the matrix that represents a derivative, this is time to enjoy and to see, oh my God, this infinite matrix, in a sense, takes derivatives. It's very nice. Now that we have the matrix, we just have these 3 elements. It's a sparse matrix. Very few numbers are different from 0. Pretty much you have the diagonal zeros and a 1/2 and a minus 1/2, a little to the right, a little to the left, next to the right and next to the left, in fact. And it goes on all the way to infinity. It never stops. So, given the crutches, we can get rid of the crutches now. And there it is. This is our guess for the matrix representation of this operator. So now we have to do the real test. The answer is a little funny. So what is the real test? Well, you know that the XP commutator is supposed to be equal to IH. So this is the same as saying that X with H over I ddx, this operator, should be equal to IH. The H bar cancels. There's a minus sign from the I's if you multiply. So this gives X ddx commutator should be equal to -1. And let's change order. So ddx with x commutator should be equal to 1, or the identity operator. So this is the question that we want to ask. All right, if I take this matrix of ddx and find its commutator with this infinite matrix, what do I get? Do I get a unit matrix? And you will see that the answer is morally yes, but not quite in a way that could be a little confusing when you first see the answer. So what are we supposed to do? We're supposed to do the dx matrix, multiply it by the x matrix, then take the x matrix and multiply it by the ddx matrix, and what do we get? Now, these are infinite matrices. You say, oh, I can't multiply those, but you could take a 3 by 3 approximation of it, or a 5 by 5 approximation of it, and multiply it and compute the commutator. You could do it with a computer, that's all right too. It doesn't take much time, and you will see the pattern emerging quite quickly. And the pattern is that you get a funny matrix as an answer. Let me see, I did overlook one thing here. It is very important, and I'm going to use it to correct it here. The ddx operator has the 1 over epsilon here, and you can't forget it. Just like the x matrix has the epsilon here. Remember, there was a 1 over epsilon there. So this 1 over epsilon must be there. Now, one thing is clear and good. The ddx with the x, when you multiply them, you have an epsilon, a 1 over epsilon, so the epsilons are going to cancel, and that's pretty good. So, without further ado, you do this multiplication, and what do you get? Well, here is the answer. The epsilons cancel, and you get a funny thing. You get this matrix, this thing is equal to this matrix. A matrix in which you get a 1/2, 0, 1/2 at the center, and then 1/2, 0, 1/2, 1/2, 0, 1/2, and it goes all the way to infinity. Pretty disconcerting, I must say. I do remember the first time I saw this and said, what did I do wrong? Well, we haven't done anything wrong. Let's try to understand it better. So, indeed, this product if something is epsilon independent and it's not what you want to get. Here you can do something that is very typical. If you get something that is not what you want to get, you write it as what you want to get plus something else, and look at that something else and wonder, why is it there? So I'll do the same thing. I will say this is the unit matrix, that is what I wanted to get, because this product of infinite matrices then taking a commutator should have given me the unit matrix, plus some matrix that I didn't want to get, and that matrix would be one with a 1/2, a little bigger, so that with a 1/2 minus 1, 1/2, then 1/2 minus 1, 1/2, then 1/2 minus 1, 1/2. And it would go on like that. So this is the center element, the minus 1. So I've put 1s all over the diagonals, and then I have to subtract them. So this is the matrix I did not want to get, and how much would I wish this matrix was not there. But it is there, and it's time to try to understand what it means, this matrix, and what it does. And what you will see is that it really doesn't do much, and in the spirit of this calculation, we will be able to ignore it. So what does this matrix do when you're acting on a function? So consider the middle row here. It would give you 1/2 of f of epsilon minus f of 0 plus 1/2 f of epsilon. This is what this row would give you acting on a function. And what is this? Well, look at here what we have. We have, this is 1/2 of f of epsilon plus f of minus epsilon. This should have been a minus epsilon, the first one. F of minus epsilon minus f of 0. But we evaluated before the sum of f of epsilon plus f of minus epsilon is at the top part of that board. And that's 2f of 0 plus epsilon squared f double prime of 0. So this is 1/2 2f of 0 plus epsilon squared f double prime of 0 minus f of 0. So the f of 0's cancel, and you get 1/2 epsilon squared f double prime of 0. So actually this leftover matrix is computing epsilon squared times f double prime of 0. So we said that these approximations that we do are good if the higher derivatives of the function are bounded. They don't grow and grow. So indeed, what our matrix relation has become is the following. I'm going to write a couple more words below. Or I think I'll do it. I'll do it here. So our relation has become the following: d dx x minus x d dx. And now I'll put here, if you were acting on a function, think of it. You were acting on a function. This really has become 1 plus 1/2 epsilon squared d second dx squared. So, given that we kept this epsilon finite, it's a regulator, it's not 0, you didn't get with these matrices that depended on epsilon, you didn't quite get the one that you wanted, but you got an epsilon squared second derivative term, and if you took epsilon smaller and smaller, you do indeed reach a limit in which these infinite matrices commute to be equal to 1, and you can neglect this as long as the functions don't have infinite second derivatives. If the second derivatives are bounded as you take epsilon to 0, this will not matter. So here it is. We had this very wonderful matrix X, which was epsilon times 0, 1, 2, minus 1, minus 2, big 0, big 0. And now you've met the derivative operator as a matrix. In fact, you've even met the second derivative operator as a matrix in here. And this derivative operator as a matrix is wonderful as long as you use very small epsilons. And this is not a useless mathematical observation. You can use these matrices to calculate things if you have a computer. Take a function that is slowly varying, and over a limited range, take 1,000 points. Computers easily handle matrices 1,000 by 1,000, and you just act with this operator, and you got your representation of the derivative. Our representation of the derivative is infinite dimensional. These are infinite dimensional matrices. You certainly could not do with finite dimensional matrices. And by the time you multiply, given your epsilon, which is thought as your regulator, the way to make precise this notion, the expected commutation relation works up to corrections that vanish as epsilon goes to 0. So we've obtained a useful representation of the commutation relation and illustrates the fact that we can think of the x and p operators as matrices, even when they act on functions.